Welcome to this video on working with functions. In a previous video we have seen how you can define functions in mathematics, and we have seen some basic functions like polynomials, rational functions and root functions. In this video we will try to work with functions in the sense that if we have two functions, how can we combine them to get new functions? So let's look at the topics in this video. We will first introduce how you can add functions or subtract them, divide them, multiply them. Then function composition, which is basically you first apply one function, say g, to some x value, and then apply another one. So we get the f of g of x. And the last topic of this video is linear transformations. If you have a given function, and how can you shift the graph either in horizontal or vertical direction, or how can you scale it? So how can you stretch it horizontally or stretch it vertically? So let's start with adding functions. Say that we have two functions, f and g, and that we now pick an x value that is in both the domain of f and g. So we can both compute f of x and g of x. Both of them make sense. Then we can define the function f plus g as simply f of x plus g of x. So then we have a new function. Similarly, we can do that with subtraction. So f minus g, then we do f of x minus g of x. We can also talk about multiplying them, f times g applied to x, that is fx times gx. And we can divide them, but with division you should always be careful because we cannot divide by 0. So this only makes sense if g of x is not equal to 0. And then we can define f over g applied to x as fx over gx. So that is the first way of combining two known functions to get a new one. The other one is function composition, and in fact in a previous video we've already seen an example of that when we were talking about crickets and chirping rates. So what we had seen there in that video is that if you have an outside temperature given in Fahrenheit, then you can relate the chirping rate, so how many times crickets chirp per minute, that is temperature dependent, and the relation is linear. So if you do 4 times the temperature in Fahrenheit and you subtract 156, then for a specific kind of cricket you will find the chirping rate. Now what we did in that video is that we said, well, we are more interested in Celsius temperatures. So what you can also do is first convert your temperature in Fahrenheit to Celsius and then use a relation between chirping rate and temperature in Celsius. And what you then find is that either you can go directly from Fahrenheit to chirping rate, that's the green arrow here, or you can make this in between step and you can first do the temperature conversion and then use the relation between chirping rate and temperature in Celsius. So what you see here is an example of function composition. So a bit more general. You could have a function g with the domain d and then subscript g. We can apply that to x. And then if this g of x here is in the domain of another function f, we can also apply f to it. So we can make one more step here, the black arrow, from gx to f of g of x. This is called function composition, and we can also do that immediately, and that's the green arrow here. And the symbol we use for that is f after g. So a little open circle, and it's being pronounced as after. So function composition f after g applied to x, that is the f of g of x. First we do g of x, and then we do f of x. We make 2 steps. Now, we have been talking about the domain of a function before, and you could try to think of the domain of f after g. So if you think about that a little bit, first we want to make the step going from x to gx. So the requirement there is that x should be in the domain of g. Next, you want to map gx to f of g of x. So gx should be in the domain of the function f. So what we find, written very concisely here, is precisely what it says above. So the domain of the function f after g is that we take all the x values in the domain of g and we pick the ones for which this holds. G of x is in df. So what that means is that we have this collection here, dg. We also have the collection df. And then if we apply the function g, probably we're going to end up somewhere here, but maybe the range is something like this collection. And then if we want to make a next step going from df, so this is g, and then I want to make another step from here using f, and I can only do that for these numbers. So these numbers are those numbers x for which gx is a part of df. And in my little picture here, we also have this area, but this area is those numbers x in dg for which g of x is not in the domain of f. So for the numbers in the area that I dashed black here, we cannot apply the function f. So they are not in the domain of f after g. Let's look at an example if this is all a bit too vague for you. So let's say that we take the function f of x as the square root of 1 minus x. And you can immediately see the domain. The domain is those x values for which 1 minus x is non-negative. So that is from minus infinity to 1. So that's all the 1 minus x should be larger or equal 0. So that means that x should be less or equal 1. So from minus infinity up to 1, 1 is included. Then similarly for g, square root of x plus 3. So the x values can be minus 3 or bigger. And then I'm going to consider the function f after g. So it's the f of g of x. So what I do, the f function is the square root of 1 minus x. So this x here, I replace it with gx. So then we get the square root of 1 minus gx. And then I plug in that I know that gx is the square root of x plus 3. So I find this a little bit ugly expression. So apparently f after g is the square root of 1 minus square root x plus 3. And then for its domain, that's what we were considering here. So using the boxed formula, it is all the x's in the domain of g for which gx is in the domain of f. All the x's in the domain of g, so that's all the x's in the interval from minus 3 up to plus infinity. And then this condition here, that becomes what it says here. So what does it say there? Let's take that out here. So what we have here, it says that the square root of x plus 3 should be from minus infinity to 1. So less or equal 1. And that gives you in the next line that x plus 3 should be less or equal 1. And then we have all the x's from minus 3 to infinity. So minus 3 to infinity. So to the right of that, that's this collection. And let's pick green here. We have that x plus 3 should be less or equal 1. So that means that x itself should be less or equal minus 2. So we also have here, say, minus 2. And then we have the collection from here, and this number is included. And then we need the numbers that satisfy both the red and the green requirement. So that is the numbers in between minus 3 and minus 2. So that is the domain of this function. So a bit more work, as you see. Let's do one more example, and then you can use the provided exercises to work with that yourself. So I'm going to do one more. So example. So we have f of x is, let's say, x squared plus 1. You see this is a polynomial, so we know that the domain of f, well, that's every real number, because I can always compute x squared plus 1. And then my g of x is going to be the square root of x minus 2. So it is easy to see that we want to have all numbers from 2 and bigger, so from 2 till infinity. So the function f after g of x, that is the f of gx. So that is the f of, well, gx is the square root of x minus 2. So plugging that in, we get the square root of x minus 2 squared plus 1. That's what f does. And now you see that we get the square of a square root. So what we get here is that we find x minus 2, because x is bigger or equal to, so I don't have to write the absolute value signs here, plus 1, which is x minus 1. Now, something tricky appears here, because this expression x minus 1, so the expression, if I would just give you that, say this is a new function, the function, say h of x equals x minus 1, you would say, well, this is a polynomial, it's a straight line, so you can compute that for every x value. So it is defined for all x in R. However, the domain of the function f after g is more restricted, because if you want to do the two steps, first g, then f, you cannot do that with every x value. Because the first step from x to gx, well, your x is special. It cannot be any x, because we are going to compute then the square root of x minus 2, and we can only do that for these values. So what we have is that the domain of f after g is f after g, well, all the x in domain of g for which g of x is in the domain of f. So that is the collection of all x in 2 to infinity, for which gx, that's the square root of x minus 2, is a real number. Well, this second condition, that doesn't say anything, because the square root of some number and x minus 2 is non-negative. You can always compute that. So that doesn't impose any restriction. So this is the only restriction we have. So that means that we have all the x values from 2 to infinity. So even though the expression can be computed for any x, the domain of the function is smaller, it is this collection, because you need to do first G, then F, those 2 steps. One more thing. I now spoke about F after G. So first we do G of X and then we compute F of G of X. You can also do it the other way around. So let's do that for this example. So I could also consider G after F. So G after F of X, that is the G of F of X, is the square root fx minus 2, which is the square root of x squared plus 1 minus 2, which is the square root of x squared minus 1. Now, the expression square root x squared minus 1 is defined for all real numbers for which x squared minus 1 bigger equal 0, x plus 1, x minus 1 bigger equal 0, sign chart. So the special values are minus 1 and plus 1, and that is x, and up here I put x plus 1, x minus 1, 0, 0, plus, minus, plus. I trust by now you know how to make a sign chart, and you can do it similarly. And we can read off that this holds true. We want it to be positive, so we have the collection from minus infinity to minus 1 included, union 1 to infinity. Okay. And let's see if we, this is basically the domain of G after F. This is the largest collection that it could be. Maybe it is more restrictive if we want to do first F of X and then G of F of X. So the domain of G after F. So the formula that was not on the slide yet, but it's the expression for the domain of F after G with F and G interchanged. So what we get is we first want to do from X to Fx. So we need all the x's in the domain of F for which F of X is in the domain of G. Because we want to go from X to Fx and then from Fx to G of Fx. So let's get a bit more space. So the domain of G after F is, well, all the x's in the domain of F, it says, so that's all x's in the real numbers, for which F of X is indeed G. So F of X is x squared plus 1, and that should be in the domain of G. So we find every x in the real numbers for which x squared plus 1, the domain of G was a set from 2 to infinity. So what does this say? It tells us that x squared plus 1 should be bigger equal 2. So x squared minus 1 should be bigger equal 0. And that is what we have done on the previous slide too. So we would find the same sign chart and so on. So the domain of G after F, that is what we had just found as the larger collection 2. So from minus infinity up to minus 1, union 1, 2, infinity. So here, if I briefly go back to the previous slide, we have found that this function G after F did this, the square root of x squared minus 1, if you combine them. That expression is defined for all x's in this set. And we see that if you do the two steps separately, first G, then f of G, that you find the same collection. So the last topic of this video is on linear transformations. And what linear transformations do is, if you have the graph of a function, they either shift it vertically or horizontally, or they stretch it, they scale it differently. So let's see for an example what we would have. And here is a little animation. So what you get is that we have the red graph and we add a constant to it. So the red graph is y is f of x, some function. The precise formula is not important here. And then we add a constant to it. And you see a little animation where I change the value of this constant. So here the constant is minus 5. So the blue graph is the red graph minus 5. And you see indeed you take the graph and it just goes 5 down. Now if I let this vary, you see that when c becomes 0, they're on top of each other. And if c is a positive number, the red graph goes up. So adding a positive number means that it goes up. And adding a negative number or subtracting a number means that the graph will go down. So this animation is also in the PDF. And if you use Acrobat Viewer to view the PDF, then you should see the animation too. Here is a static image because then you don't have to see the animation anymore. So here's the original graph. And I have plotted +3. And then the graph goes up. And I've plotted y is fx minus 3. And you see that the graph goes down there. You can do the same in horizontal direction. But you should take care because that is a bit counterintuitive. Because here, if you have, here I put the number 5, for instance. And then it says x minus 5. And if you do x minus 5, it goes to the right. If you put there f of x plus 5 or another positive number, it goes to the left. If you think a little bit about that, you will see that if you do x minus 5 and you plug in x equals 5, then you're in the origin again. So you have to work on this a little bit yourself. Maybe draw the function y equals x squared and then see what happens if you do this transformation. But note the minus sign here. And again, this is the animation. For c equals 0, you see that they're on top of each other. And here I put a static image. So the red graph is the original one. If you do in black f of x plus 5, it moves to the left. And in green, y is f of x minus 5, and then it goes to the right. So that may be a bit counterintuitive. So spend a little bit of time with that to see if you can understand why that holds true. Then scaling, what you see here is a function and I multiplied that with a number. So I just put c times fx and c is varying here again. You now see that if c equals 1, the graphs are on top of each other. And what this basically just is just stretching in the vertical direction. So if I take the stationary images again, you see the function and 2 times the function. So the blue graph is 2 times the function. And what is basically happening here is that you put different numbers on the vertical axis. So it's stretching in vertical direction. And here you can also stretch in horizontal direction. And here you see what happens. So if you multiply with a number, then the graph goes steeper here. So these are simple transformations of a function that are good to know. So what if we see, oh, sorry, this is the stationary image. So red is the original graph. And if you do y equals f of 2x, you see that it goes up faster. It's a relabeling of the numbers on the horizontal axis. So what have we seen? We have seen if you have two functions that you can add, subtract, divide, or multiply them. If you divide, you should take care that you are not dividing by 0. We have looked at function composition, first doing one function, then applying another function to the result. And then we looked at these transformations. So vertical translation means that your function moves up or down. Horizontal translation, function moves to the left or to the right. And then scaling means that you're basically stretching either in horizontal or in vertical direction. So I hope all was clear, and I like to see you in the next video. Bye for now.